Question 2 says, a region S lies between the curve y equals x squared and the horizontal line y equals 4. The region is bounded vertically between their points of intersection. Part A says, find the total area enclosed by the region S. And they've given us a nice little graph over here. So the region S that we're going to find is, of course, this shaded region here. So what we're going to need to do is we're going to need to set up an integral that works with what they've given us. Now, it does tell you what each of these are here, but let me just write this out here. Y equals x squared is our parabola, and y equals 4 is our horizontal line. So anytime you're asked to find the area between two curves, you really just need to remember the integral of top minus bottom. In other words, what we're going to do is we're going to figure out what the top function is and what the bottom function is in this shaded region here. And I think you can see pretty clearly that the top function is going to be y equals 4, and the bottom function is going to be y equals x squared. So when we go to set up our integral here, it's going to be 4 minus x squared. You don't really need these parentheses here, but for more complicated functions, it's very helpful to use. Now the other thing that we need is we need the limits of integration. Now, as you look over here at the graph, you'll see that, of course, there are a couple of places, 2 places in fact, where these curves intersect. We need to figure out what those places are. In order to do that, we're going to take our 2 equations and set them equal to each other. So we're going to do x squared equals 4. This is a pretty simple equation to solve. Take the square root of both sides. You get x is equal to plus or minus 2. That's what's going to go down here. Now we can evaluate the integral. Now there's a little tip I'd like to show you. This is something you can do with integrals. You can use symmetry to your advantage. What we're going to do here is, instead of going from -2 to 2, we're actually going to go from 0 to 2, and then we're just going to double our answer here. The reason why this is a more effective way, more efficient maybe I should say, than -2 to 2, is because at some point we're going to be plugging in our limits of integration. And if you can plug 0 into an equation, well, usually 0 is very easy to work with. Let's see what happens when we do this. Okay, so we've got our 2 in front. Then we need to find the antiderivative. So we just need to add the x here, add 1 to the exponent, divide by that number over there, 0 to 2. Now we need to plug in our limits of integration. And here's the beautiful thing. When we plug 0 in for x, that's just going to give us 0. I don't even have to worry about plugging that in. So I'm just going to plug 2 in. 2 cubed. It really just boils down to us doing the math here at the end. So 4 times 2, that's obviously 8. Here we have 2 cubed, that's 8 times a third. Well, that's 8 thirds. Let's see here. We're going to need a common denominator here, which is going to be 3. So if I multiply that by 3, that'll give us 24. 24 minus 8 gives us 16. And then finally 16 thirds times 2 is 32 thirds, and thus we have our final answer. Part B says, suppose region S is rotated about the x-axis to form a solid. Calculate the volume of the solid. Well, all right, let's come over here. Let's draw a little arrow here indicating that we're going to take this shaded region and rotate it about the x-axis. Now, this is a solid of revolution question. That means we're either going to use the disk method, the washer method, or perhaps the shell method. Now, in this case, we're going to be using the washer method, which looks like this. This is the formula, that is. Like that. So here's what we're going to do. We're going to come over here to this graph. and we are going to draw a rectangle. This rectangle is going to be bounded by the two curves of our shaded region. And you can draw the rectangle anywhere. I'm going to draw it, I think, right here like this. And I'm going to put this rectangle perpendicular to the axis of rotation. Now, this is the interesting part here, because what we're going to do is we're going to try to find the distance from the axis of rotation to the furthest point of the rectangle. So we're going to call that capital R. Then we're going to find the distance from the axis of rotation to the closest point of the rectangle, and we'll call that little r there. So that's what we're going to try to find, big R and little r. So when you've got this set up like this, what you want to do is you want to come over here and you want to think about what we did in part A. Remember in part A, when we were finding the area of the shaded region, I said to think about top minus bottom. And that's what we're going to do here. To find r, think about the top function and the bottom function. The top function is just y equals 4. The bottom, if you will, the axis of rotation, is just y equals 0. So that means that the top of this, right, the distance from the axis of rotation to the top of this is always going to be just 4. Now the same idea is going to apply to the bottom of the rectangle I drew. But this time you can see that the bottom of the rectangle changes based on the blue y equals x squared. So that means that little r is just x squared like this. So what we're going to do is we're going to take our integral. And now that we know big R and little r, we're going to plug that in down here. Big R is 4, little r is x squared. We already know what the limits of integration are from part A. It's going to be negative 2 to 2. Okay, so let's see what happens here. We have 4 squared, which is 16. We have x squared squared, which is, of course, x to the 4th. There we go. And we can do the same thing that we had done before. We can use symmetry to our advantage. And what I mean by that is, instead of going from negative 2 to 2, we're going to go from 0 to 2, and we're going to double our answer. Okay, let's see what happens when we do this. Our integral is going to be 16x minus 1/5 x to the 5th. And of course, we're going from 0 to 2. Now here's the beauty of doing the symmetry here this way, is that when we plug 0 in, we're just going to get 0. So we don't even have to worry about that. All we have to do is worry about plugging 2 in. So here, let's go ahead and plug 2 in and see what happens. Okay, 16 times 2, that's 32. 2 to the 5th is 32. So we have 32 over 5 right here. We're going to need a common denominator of 5 here. Okay, so that means I have to multiply this by 5, which is not the nicest number in the world. Looks like it's 160. So now what we need to do is 160 minus 32, which is 128. 5. And then, of course, we have our 2 pi at the beginning, so we got to do 2 times 128, which is 256. We can just leave the pi there, and we get our final answer right here. Part C says, there is a horizontal line, y equals c, or c is greater than 4, such that rotating region S around this line produces a solid with the same volume as in part B. Write but do not evaluate a definite integral that could be used to find the value of c. Okay. So, of course, a horizontal line has to be, let's see here, greater than 4. And just so we remember, this is the line y equals 4 here. So that means that there's some other line, which is above here. Let's just put it like here for a moment. And we're going to rotate our object around that line. And evidently, we're going to get the same volume as we did in part B, depending on where we put this line, and we need to figure out where this line might be. So let's call this line y equals c. Then let's go ahead and draw in a rectangle, just like we did last time, in the shaded region here. And now what we're going to do is essentially the same thing that we did last time, which is we're going to try to figure out what is the distance from the axis of revolution to the furthest point of the rectangle. That'll be capital R. And then we'll try to find the distance from the axis of rotation to the, the closest point of the rectangle, and that'll be little r here. Once we figure that out, we will plug that into our formula for the washer method over here, r squared minus r squared. All right, so remember what I said last time. You want to think about these like we did in part A, top minus bottom. In this case, the top function for both r's is going to be c, but what's going to change is the bottom function. So big R here is bound between c and this parabola here. So what we've got is c minus x squared, right? Top minus bottom. Same idea for little r. Top minus bottom is going to be c minus 4 this time. So these are going to be plugged into our formula over here. So we've got pi, and then big R squared minus little r squared. Big R is c minus x squared, and little r is c minus 4. Our limits of integration are to go from -2 to 2 here. And because we don't have to evaluate it, we can just leave it like this. Now, having said that, this is kind of a silly thing to say. We do know what it evaluates to because it's supposed to have the same volume as part B. And in part B, we figured out it was 256 pi over 5. So we actually can evaluate it. This is what it should be equal to here.
If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.